So today we're going to look into system identification from a transient or a step response. And even though it's a lot easier to determine a linear system from the frequency response, because the poles and zeros can easily be seen, and things that are far apart can be seen because it's plotted on a logarithmic scale. But to generate a Bodie plot from a real system, one method is to put in a sine wave and measure a sine wave, put in another one and keep changing the frequency and measuring the output. And that is the most reliable way to generate a Bodie plot. But you have to take quite a bit of data, right? Now, yeah, Scopy has a kind of a Bodie plot generator, and it's actually can be fairly quick, right? But if you're testing a lot of things, or if you're testing something with a lot of low frequencies, right? If you're testing a system where, 5 tau is a second, right? It's taking you a long time to take each data point, right? Because you have to input the sine wave and let it settle for some time and then do the measurement. Also, putting in a step into a system can be an easy way to tell you what that system is and what you're looking for. And also, if you can put in a step, you can take the derivative of the step and take the FFT, and take the output of a system from a step, take the derivative and take the FFT, and then take the ratios of these two fast Fourier transforms and get the Bodie plot. But they can take some interpreting, because there can be numerical artifacts that can make you wonder what it is you're really working at. All right. So we'll go through some simple things, then we'll get to second order, and then I'll show you a case study where it turned out that this was really important. All right. So we have a Desmos link. Where I have programmed a square wave based off of a step response, right? And then I have some various things, right? And so if I'm integrating a step, right? So convolving a step times a step, right? If I looked at the transient response, I would see this kind of ramp upwards, right? But if I were to take the differential of that step, that's a little bit ugly in Desmos. But really, S in the frequency domain is differentiation in the time domain. And so this step up it'd kind of go to infinity and back to zero. But really, like low pass filters, when you're in the roll-off part of the transfer function, are actually acting like integrators, and high pass filters, when you're when the magnitude is increasing, let's say 20 dB per decade, it's acting like a differentiator. All right. And so if you have a constant slope and take the difference of it, you're going to get a constant L. If you have a constant slope and integrate it, you're going to get something squared. Okay. That's just more review and helps with the convolution. That really, as such, won't be a question on the final exam. But it helps. It does help with the final exam. All right. So here we have our low and high pass filters. And right, that the high pass, right, goes to 1 and decays in 5 tau. The low pass starts at 0 and increases to 1 in 5 tau. All right. And when omega is big, tau is smaller. So this one has a bigger omega or a smaller tau than this one. And so I'd rather. So this is more like question 5 from midterm 1, where this is HT low pass. This is the Bodie. And if I have something with a smaller tau, that means that omega naught is bigger. Now, it can be hard to test this. So a lot of times what we do is we look at H step. Okay. And that the one with the larger 5 tau is the one that takes longer to charge. The one with the smaller takes the smaller. Okay. And those are, relating the time domain to the frequency domain. All right. So, but, what does this look like? We can analyze this a little bit better. So let's say we have H of S. I'm just going to make up a low pass transfer function. And we can have a high pass transfer function. And we want to know what the step response is going to be, right? We want to estimate it. Well, V out S of step, the step will equal 1 over S times 100, S plus 100, V out step. Okay, now what we can do is estimate how the time is going to be at 0, and time is, much, much greater than 0. And what we do is we multiply by S. And you're going to think it's a little bit ridiculous. We just multiplied by 1 over S, and now we're going to cancel it out. But this works for, what if I was inputting a ramp, right? Then I would multiply by 1 over S squared, multiply by S, and then I would have what was left, right? But it's also really convenient that the transfer function, right, we can kind of tell what's going on. And right, so if we let S and kind of go to infinity, that will be like when VT equals 0. All right, so let's cancel these out and let S go to infinity. Then that term will go to 0, which is exactly what happens. All right, and if we want, if we let S go to 0, then VT as it goes to infinity, right? So S is 0, 100 divided by 100 is 1. It's 1. So we actually get these 2 points. And by now you probably recognize that that's a first order, right? The denominator is telling me it's a first order. And so that 5 tau would be 5 divided by 100. And that's how long it would take to go up. I'm just going to scroll down a little bit and rewrite the high pass part. Okay, what's the step response? All right, we multiply by S, but then we want to know what's happening at low at time equals 0 and time equals infinity. So we multiply by S. So that all cancels out. So now we let S go to infinity. All right, then H of S, infinity plus 100 equals 1. And then S, if we let that go to 0, it's going to be 0, 0 plus 100, or 0, right? Right. So when S is infinity, time is 0. When S is 0, time is infinity. And so we have our 1, we have our 0, and we know that it's exponential decay. All right. So if you were asked why, right, you would use this methodology to tell me why it's high and low, right? Or why does this match the Bodie plot or the transfer function of a high pass filter. All right, now let's look at some other shapes. So this is a low pass, right? And now we're just comparing. And you can see here, I can see 2 breakpoints. It's definitely overdamped. Here, I programmed it to have 1 breakpoint, but even if they're very close, right, it's critically damped because I can really only see 1. And then here I have an overshoot. And so in fact, it's underdamped. Now, as a review, you don't have to see a peak for it to be underdamped. For a second order system, if the cutoff frequency is minus 3 dB down, it's actually underdamped. On the other hand, in the time domain, notice this is our overdamped, and one pole is at 10 near 10 kilohertz, and the other one is over 1 megahertz. So one is much faster than the other by a lot, and this almost looks first order. Okay. If you was zoomed in here, you could see a little S shape and you'd know it was second order, but it's kind of hard to tell. All right. But you'd know that it was the step response of a low pass filter. You would know that it is certainly not underdamped. Now here is the critically damped response, right? Again, no overshoot. So it can't be underdamped. And here is some very obvious overshoot. Now, while there doesn't have to be a peak in the Bodie plot to be overdamped, if this signal goes even just a little bit peak and settles down, no matter how tiny, in the transient step response, it will be a little bit underdamped. All right. So questions on the final, you'd get something like this. You'd get one of these curves, and you might have to match if you got all of them. But, take the blue line. Is this over, under, or critically damped? And you'd say, well, it's not underdamped, and it's a low pass filter. Why? Well, then you would use the logic of, well, at time equals 0, it's 0. And if I multiply the step response of a low pass filter in the frequency domain by S and let the frequency S go to infinity, I get 0. And then when I let S go to 0, I would get 1, which means time is infinite. That would be Y, right? Here, now these two lines might look different, but if you only see one and I zoomed into here, it might be very hard to tell. All right. And of course, any peaking at all would be underdamped. Now here we have the high pass, and it's a little different. All right. And what happens is, in the low pass, it's the low frequency pole that's dominating. And so it takes a long time to come up. In the high pass, right, see how fast the step response comes down? You can barely even see it. That's because in the high pass, it's the higher pole that's dominating. Then when we look at critically damped, no overshoot in the time domain, but there is an overshoot in the time domain for the high pass. So it overshoots and comes once. The difference for the high pass is it can go below and settle back, but if it crosses again and comes down, then it's underdamped. And of course, a lot of oscillations is very obviously underdamped. Then we have the Bodie plot of the band pass. You can see various damping ratios, right? And the red, in this case, is being dominated by the slow pole, if you will. And it almost looks, though, like the step response of a high pass filter. You'd have to zoom in to see that, in fact, it doesn't go to 1 right away. And in the critically damped, it's even more obvious. You see it kind of go up and then come down, and it doesn't quite go to 1. And then for the underdamped, you can see the oscillations. Now, on an exam, I wouldn't give you something that tricky where, we're doing it over an internet connection, or I had printed it out. It'll be obvious, right, that it's a band pass. Okay. And for the notch, again, it's the slow pole that dominates. But notice the notch starts in the middle, or starts at 1, goes down and comes back up, right? So the notch, right, has, look at the underdamped or the overdamped one. It has, actually, if I zoom in here, it's got the high pass step response of a, okay, so let's go back here. Right, see the red, it's so quick. And the high pass one is designated by the high frequency, the high pole. And notice it goes from 0 up to 1 and comes right down in that quick amount of time. But then it's also got the low pass response in it as well, right? So with the notch in this kind of obvious way, you're getting both responses. Where with the underdamp, it just kind of is oscillating on you. And the critically damped, it goes up some, it goes up to 1, but it doesn't go all the way back to 0, right, before it starts rising again. And this doesn't exactly go back to 0, but it's kind of hard to tell. All right, but these shapes, right, if I were making an equation sheet for the exam, I'd probably try to write down and understand what's going on here. But there's some things that I can get where if once I recognize this is a notch, right, and it goes to 1 for a 1 volt step, that means the gain DC is 1. And if, notice how in this one, the gain, I mean, it goes up to 1. Well, that's kind of indicating that the gain is for the high pass is 1 as well. And if you were to zoom in on this, you would see that all 3 of them start at 1, which is the high frequency part, which would mean the gains are all 1 here. You can see they all settle to 1, which would mean all the DC gains are going to 1 as well, right? And that you'd have some second order transfer function. Now, yeah, interestingly, all 3 of these have the same omega naught. The difference is the damping ratio. So it can be hard to estimate omega naught, but you could, the fact that it goes almost to 1 is what happens when it's overdamped by a lot, right? Because the damping is 10. When it's critically damped, zeta is 1, it goes down somewhat. And when it's, very underdamped, you can start to see that oscillation right away. So you could say, is it, you can definitely say whether it's over or underdamped, but then you can make estimates as critically or overdamped. But to actually numerically find it, I used to have notes on this, and it is really tricky. Okay, so it's not so important to be able to get the exact answer. What's more important from the time domain is, do I have a second order system? Is it low? Is it high? Is it band? Is it notch? And there's other kinds of transfer functions as well, right? But in 110, I'm prepping you for filters, so that's why I concentrate on filters. All right. Now, let's take, what I want to do is take a real world example, right? Where this is a Bodie plot of a low pass filter. And I used, this was before the pandemic. So I was using a function generator, and I would set a sine wave and then use the oscilloscope to measure V in and V out. And I had it all programmed in Python. And to generate that plot, 5 minutes, because I had to sample it a lot to get it to get rid of the noise. All right, so even though it was automatic, it would take 5 minutes for this plot to run. Right, and so here the blue line is the magnitude and the dots are the phase. And yeah, the phase where the function generator only goes so high, right? But it really looks like it's a second order low pass filter. All right. The phase is going almost to minus 180. And you might just think, well, I just need more frequency, right? If I were to look at the slope, I could see a minus 40 dB per decade, right? So it's looking, second order low pass. But in a real world measurement, the phase is very hard to measure. So because it's going from 0 to a negative number, it's a second order. But also because it's going to the negative number, it's not inverting. All right. So that, but then when it comes time to pick omega naught, I kind of just use the asymptotic method and pull off omega naught. Let me move this out of the way. It's 350 kilohertz, right? Then I pull the gain from 350 kilohertz, and it was about -5. So the gain at omega naught, right, is 0.56. Then I put that into my damping coefficient and I get 0.89, right? The Butterworth conditions would be 0.707. So it is a second order filter. It is underdamped, but notice there's no peak. If it were critically damped, it'd be -6 dB down. Okay. Anyway, so that's good, right? Measuring, putting in a sine wave at those various frequencies, and you can see how many frequencies I use because each dot is one frequency, right? Well, that's great. So I go, and since, I'm always got to use LT Spice somehow, right? I had an R, L, and C, and I wanted to make sure that I was matching what I was getting. So I read in the data, right? So there's the measurement, and then there was the data here, and I tweaked everything until it matched. All right. So that I was pretty sure my second order RLC, it had 77 ohms, 20 microhenries, and a large capacitance. Okay. Now I'm going to verify the transient response. I have these equations here, and for when zeta equals 0.89 and omega naught equals 2 pi times 350K. And notice there is this little overshoot. So it is underdamped. Wow, this is great. Everything is matching. Let me measure it. Everything falls apart. So the green, right, is in fact supposed to be the output of the circuit of a step response. But notice there isn't an overshoot. And because that was weird, I wanted to check the input. Can anybody tell me what this looks like based on today's lecture, the yellow? Just shout out a guess. What system is that?
A notch?
Yeah, it's a notch. Now, I don't have a picture, but I can tell you I knew how to hook up that circuit. And V out is certainly a low pass filter. This is V in. So what do? I disconnect the circuit and make sure that I'm getting a step response. So when the circuit isn't connected to the function generator, I am getting a step response. I hook it up, I'm getting a notch. I disconnect it, I'm getting step. I connect it, and I'm getting a notch. So when you connect up a circuit to the function generator and it changes V in, well, something's going on, right? And what it is that function generators have a 50 ohm series resistance. They all have it, and it's done on purpose. So now if I add that 50 ohm and model it better and then do it in LT Spice, lo and behold, I am getting the same thing. All right. But this Bodie plot, it was real. That was a real Bodie plot, and it worked. And I verified it against LT Spice, and it still worked. But when I try to measure the step response, it's not working. Well, the thing is you're probably already thinking what a fool I was to use R1 of 77 ohms, because the voltage division here is not, it's going to cause problems, right? But if I go and find out what is the node voltage here, what's the transfer function here, right? So even though it's a little bit weird, I have R1, L1, and C1. So I have the series resistance, right? I have these voltages divided from the whole. And when you work through, it is a kind of notch filter. It's not a perfect notch filter, but it certainly behaves like one. And so the reason why the Bodie plot worked is because I didn't assume what VN was. I measured V out, the magnitude and the phase, and I measured V in, magnitude and phase, and what would happen, and then take the ratio. So that even though, right, I'm getting this notch response here, right? That means the input to the system is changing with frequency, right? The magnitude is going down, the magnitude is going up, but because whatever the input was, I divided that by the output, I couldn't tell. It was fine. It wasn't until I did the step response. All right. Now imagine if I use the frequency right at the notch frequency, something would have happened, and I would have gotten a bad value. And maybe that could explain some reason why I had to skip over a value or two. All right. But that's kind of how I use system ID in the transient domain to try to figure out what's going on. Right. And so if you now know, like when we talk about advanced summers, I also talk about why you want to make sure that your outputs for the op amps are always 2K, right? And no less than 2K. This is part of it, because the function generator, right, when you go to test it, it'll really mess up your results. Okay. So this is kind of why I make a big deal out of it. Oops, I guess that's it. So really, if on the homework, you just have to go through and it's more estimate. What kind of filter is it? High, low, medium, right? Band, notch, pass, or notch, right? And then get an estimate of what the damping ratio could be. That's pretty much it. Okay. Where on the Bodie plot one, no, you got to find, what kind of filter it is, and the game. Everything can be known from the Bodie plot that I give you. All right. Now, are there any questions on this?
Yes, I got a question.
Yeah.
Okay, I think I'm still on how to tell what kind of filter something is and whether it's first or second order, but dynamic coefficients are where I don't completely understand. I guess we can basically just estimate whether it's over critically or under damped, but it's not always easy to tell which one it is when it is.
For transient or
Transient.
um, yeah, the transients are quite difficult. And if you see the way I ask the questions, it's more like, what is it, over, under, or critically justify your answer? And but if you go, that's why, like for the low pass, right? For the low pass, if there's no overshoot, then it is critically or overdamped, right? But for the high pass, it changes. If it crosses zero, if it crosses zero once or less before it settles, in fact, it's not underdamped either. The overdamped won't cross at all, but near critically damped, it'll cross one. Actually, there's a range, right? But notice the underdamped has a lot of oscillations. And I try to make sure that when I ask a question on an exam, like I have a lot of oscillations. Like I'm trying to be obvious. Okay. Now then with the band, right? It's the red one on its own. It would be hard to tell low pass or high pass. I mean, high pass or band pass. But the blue one, you can see that it takes a certain amount of time to come up and then come back down, right? And then the band, right, because it's attenuating the DC, it goes back to zero, right? And then for the notch, you're getting the high and the low pass together. So they start at one and they end at one. And how do they get there? Right. But, in this case, yeah, this is wildly overdamped and it almost goes back to zero because these two poles are very far, these break frequencies are very far apart. So they're almost not interacting. But on the critically damped, they're much closer. In fact, they're repeated in the same. So you can kind of see that. And then for the underdamped case, well, you see the oscillations. But they're kind of graded forgivingly, let's say. It's just your estimate because you would almost just have to come up with an equation and backfit it to the whole thing to see what it was. Like start guessing omega knots and damping ratios and play with them until you got what you wanted. Unfortunately, there'd be more than one right answer. There's probably more than one omega knot zeta pair to make things look similar. Okay. Does that help?
So for Dan, so basically we just take an educated guess, and as long as we don't miss anything obvious and we put actual effort in, it should be okay, right?
Yep, that's it. Okay. So but yeah, I mean, here are these notes, which, I think could be used as a case study while you're doing the homework. Okay. So I finished grading the exams, and at some point, I realized a lot of people were getting the gain bandwidth one incorrect. Not quite sure why, but I thought that would be today's review. All right. I mean, anyway, so we have this problem, okay? And the transfer function of the op amp, right, is this V out equals, and it's a second order function, right? V plus minus V minus, right? So that's the transfer function of the op amp. And then I'm giving you some values. R1 is 10K, C1, R2, and R3. And yeah, R3 is 0, which turns this into a wire, which makes the gain equal to 1, right? Because by inspection, it's a non-inverting gain stage. All right. Now then I could ask the question, derive the relationship that will make the transfer function of the whole circuit be 100 divided by S plus 100, or a low pass filter, which if you looked at the RC values by itself, this would be a low pass filter with a transfer function of 100 divided by S plus 100. All right. Now the thing is if you want the whole circuit to be that, well then V out has to equal whatever this is. And that means this has to be acting like a unity gain buffer. Now, what are the conditions? So here's the thing. Many people what they did is they said, well, that I recognize it's a non-inverting gauge stage. And so that's this. They plugged in the values and then just calculated the gain, right? But I'm giving you H of S of the op amp. It's got a frequency dependence. Open loop gain is not infinite. So you can't just say that. You need an equation or a relationship, and it's got to be something with frequency, right? Because, right, here's that equation plotted out, right? This is changing with frequency. And if the gain is 1, well, this is where it's going to stop working, or nearby, right? Graphically, I'm asking for an equation, but you need a frequency range, right? You need to be able to interpret that you needed a frequency range. All right. So anyway, so really, I don't have to care about this. I really just need to know, when will the gain of this be 1? What frequency will give that to me? All right. So you got to come up with a Q of S, or you could call it the H of the non-inverting op amp, right? And that would be V out divided by V plus, right? Because that's V plus. That would be the Vx. But I converted it into a system flow diagram, and I just write it out, the HS of the op amp, 1 plus beta, HS of the op amp, such and such. Now, this is something else I have to point out. I'm just going to use, I'm not going to do, I'm going to change the numbers here, right? Beta, what is being fed back in, right? That's my plus, that's my H of S, right? What's being subtracted, right? Well, it's the voltage division, and that's going to be R1 plus R2, right? But some people were just calling beta equal to this. No, 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 no. Okay? Don't do that, please. Now, yeah, in this particular example, you could have done it either way and it wouldn't have mattered because if beta is 1 over beta is 1 and could have gotten away with it. So you multiply everything out. All right. And we get Q of S, right? Or it's H of S of the non-inverting op amp, meaning it's the op amp hooked up with negative feedback. All right. So now, if beta is equal to 1, here's my equation. And really, in order for this to equal 1, the 100 megs have to cancel out. Well, how's that going to happen? Only if the magnitude of this is less than the 100 meg. Okay. And so you can just write that out like here, those upward pipes are just the magnitude is less than 100 meg. And that's all you had to say. All right. Of course, I took it a little bit farther where, all right, let's calculate, and you can come back later to look at this yourself, but let's come up with this equation. Let's multiply everything out. And I went and found the magnitude. Of course, that's the square root of it, which makes it kind of hard to evaluate. So I square both sides and I come up with this kind of equation, which it is a bit of a monstrosity where I have omega to the fourth plus something times omega to the second plus a constant, right? But anyway, Python, right? I just put in those constants into a fourth order coefficients and it spits out these roots, right? And so I have something imaginary, a negative frequency, and a positive frequency, which is close to 1K, right? So the only one that makes sense is the one that's 999 radians per second. All right. So if this is the Bodie plot, right, of the open loop gain, no, I guess I changed it. Here's the Bodie plot of the open loop gain. And if you were asked to do it graphically, you'd see, oh, there's, if I need a gain of 1, this is where the transfer function of the open loop op amp is 1. So it has to be less than that, right? And you, although in practice, it is smaller than that, right? Because that it'll roll off, but that's a good estimate, right? The frequency has to be lower than that. And what I did is there's a link. This has the file and you can download that link. All right. Now then, okay, that's the relationship, because if this is much smaller than this, it drops out 100 meg divided by 100 meg, right? It's 1. So now I came up with the frequency, but you didn't have to do that, because having to deal with a fourth order root on an exam is kind of a pain. All right. Now then, what is the over under critically damped? Well, you take the denominator of QS, right? Multiply everything out and then use the quadratic equation, and you see that 100K squared is greater than 4 times 100.1 meg, right? So it's overdamped.
Of intel inside the Western.
Okay. So that being said, some people, they took the HS of the op amp, and in this case, let's just write that out. And they did the analysis on this, and they calculated overdamped. Well, yeah, it is, right? Because you can see the two real poles right there, right? And so, but that's of the op amp. You have to operate on H of S of the circuit, right? Which would have been this, which we could also call Q of S. All right. So for today, so those were like, a lot of folks had used the wrong H of S, and some, were just kind of spitting back the non-inverting gain. The assumption is now we're in 110 and we now know about gain bandwidth. So unless, you're told that assume the op amp is ideal, you're going to have to work on this, right? Especially because that was the gain bandwidth question, right? So you're going to expect some kind of gain bandwidth. All right. So okay, so that's the question, right? We have 90, 10K. I'm leaving this part out. What's the mathematical relationship to make that gain equal to 10, right? We know it's a non-inverting op amp, and that 1 plus 90 divided by 10 is going to be 10. And then is it over, under, and critically damped? Which only makes sense if it's a second order function. If it wasn't, you can't really ask that part. All right. Okay, so does everybody have the question? Or I'll just give it 2 minutes to everybody to write down that question. All right, that's 2 minutes for me. So I'm gonna open the rooms and go to the rooms. Again, it's not about just a technical thing. It's about meeting people and saying hi and feeling connected. Okay? And I think every room has enough people. All right. And let me. All right, so here's a rough solution, right? Basically, beta is R1 divided by the sum of the two resistances. So you don't even need the units. It's 10 divided by 100.1. All right, which can change, right? If you get that wrong, then the over, under, and critically damped would be wrong. Here's the HS of the op amp, right? Q of S or the H of S of the circuit, right? And it's just that classic control equation, where you have a summer and a transfer function and then V out, right? So I just write that out, multiply through the denominator through, and I get, this is the equation which I have to operate on, right? And so alls I would expect on the exam, if it was to do it mathematically, is to take the absolute value or say the magnitude of this is greater than 1 meg, right, for a gain of 10. When that happens, this will drop out compared to the 1 meg. 10 meg divided by 1 meg is a gain of 10, right? Then for the over under critical, right, we just look at the denominator, right, multiply everything out. And yeah, 1 is so much less than 1K that when I add these two together, I'm just putting 1K. It's an approximation, right? And when I add this 1K to 1 meg, yeah, it's 1.001 meg, but it's not really there. We use just a version of the quadratic equation. B squared is a greater, less than, or equal to 4AC. And in this case, it's less than, so it's underdamped. Okay. So, next time the review problem will be the control one, where you have an out of control transfer function and you need to fix it. Okay. And we will continue with Fourier applications. All right, I'm going to stop sharing and stop recording. And if anybody, somebody did want to stay behind and ask a question, so I'll just wait for that.